All right, so we're going to study. What was the last chapter we covered? 27, I think it was, on parallel series and parallel circuits. We've already had a little bit about series and parallel with capacitors, but it's completely different, or it's different when it comes to resistors. And so we're going to study that in tonight in these experiments. Hopefully we'll do like 4 circuits. For sure we're going to do at least 3 of them. The series, the parallel, and a series parallel combination, at least one of them. If we can do it quickly, we'll get to both of them. So these are all the things that we're going to need to get it done. Just some general comments. For all of the circuits, I want to use 10 volts. It'll just make the calculations easier. So let's keep the power supply at 10 volts. Last time we varied at 5, 10, 15. Let's keep it, all the circuits or all the power supplies at 10 volts. I want 3 different resistors. As a matter of fact, I've already picked them out. Who can tell me what a brown, black, red is? It's a 1, a 0, and a multiplier of 10 to the 2. So this is 1,000. I chose 1,000. Green, blue, brown is 560, and then I've got an orange, brown, which is 330. So these are the resistors that we're going to use. The note I have here says select the resistors in the range of 100 to 10,000. I've already done that for you. So the largest value, the 1,000, is R1. The next one, 560 will be R2, and the 330, the last one, will be R3. And we're going to use these same resistors throughout the experiment. Now, somewhere on your paper, I want to see your calculations on how you get the equivalent resistance, and how you calculate what the expected currents are for the circuit. Okay, so here's just a general discussion. When 2 more resistors, or light bulbs in this case, the way this figure does it, these figures come from G and Coley, a textbook I used to use in the past that I like, and I had already had this set up, so I just copied it. When they're connected the way shown, they're said to be connected in series. The equivalent resistance is very simple when they're series. You just add up the resistors. As the figure shows you, the equivalent resistance is R equivalent is equal to R1 plus R2 plus R3. Since there's only one circuit, if you notice, can you see? Yeah, you can see on there my cursor. There's only one current. There's only one path for the current to go. So it's going to go through all the resistors. Since there's only one path for the charge to flow, there's only one current that travels through each of the resistors. The voltage measured across each resistor will be capital I, Ri, where the I is the subscript for the resistor. So the total voltage is IR1 plus IR2 plus IR3, and you'll get 3 voltages, and that should equal the total. Now let's do an example. I have 2 45 ohm light bulbs and 190 ohm light bulbs. They're all connected in series. So what's the total resistance? Very simple. 45 plus 90 is 180. Now let's assume that we have the 10 volts, and we want to know what the total current is. So 10 volts divided by 180 is 0.0556 amps, or 55.6 milliamps. Now that we know that current, there's going to be a voltage drop on each resistor. If you remember Kirchhoff's law, when you do a loop, you start with the battery, the power supply, and then you calculate the drop across the first, then across the second, and then across the third, and come back to the battery. So if we do this, not now. If we do this, we get 0.556 amps times 45, 0.556 amps times 45 again for the second resistor, and then 0.0556 amps times 90. And that gives us 2.5 volts, 2.5 volts, and 5 volts. Lo and behold, it's the 10 volts total that we get. These are the kind of calculations I want you to be doing as we go through this laboratory. Okay, now resistors in parallel. When two or more resistors are connected side by side with all of their ends common at common nodes, as shown in Figure 2, the resistors are said to be connected in parallel. This is maybe where on the previous one I handed out, it may say figure question mark. You can check that on your if you have the one I sent out. I'll send out a previous one. I don't know what it's talking about. If I can't be found. Okay. Now, if I were to take a meter and I put the positive here and the negative here, and I move the positive around, it's going to be the same voltage. The same voltage. So in this one, where we had a single current, we have a single current, but multiple voltage drops. In this one, we have a single voltage of the same voltage across all three, but we have different currents. We have I1, I2, and I3. We have three different currents. So this is for parallel circuits. So R equivalent is you add up the reciprocal resistances, but you're not done there. And a lot of students trip up on this. What you've just calculated, if you add the reciprocals of the resistances, is you get 1 over R equivalent. You have to take the reciprocal of that to get the correct value. And that's why I like using this second, the right half of equation 3, R equivalent is equal to 1 over, and then the sum of the reciprocals. So the single current coming from the battery splits into separate currents for each branch. The voltage will be the same across each resistor. So each current is calculated by I sub I equals V R sub I, where the I subscript determines the current for the particular resistor branch. Let's calculate the equivalent resistance results for the following example. Again, we're using the same ones. 245 light bulbs and 190 ohm light bulb are connected in parallel. What's the total resistance? Well, you can see here. Can I make it bigger? Yeah. I'm using the right-hand formula, 1 over the sum of the reciprocals. And those are easy values to calculate. 2 over 90, 2 over 90, and 1 over 90. So you get 1 over 5/90ths, or 90 divided by 5, which is 18. So we've got a total equivalent resistance of 18 ohms. We went from 180 down to 18. So just by combining them in parallel, we've reduced the total resistance that the battery sees, that the power supply sees. So if we calculate the total current, we take our 10 volts divided by 18 ohms, we get 0.556 amps, or 556 milliamps. So now let's calculate the current in each resistor and sum them to verify the total current. So the total current is equal to delta V. Now remember, the delta V, it's 10 volts for all of them. So it's delta V divided by R1, delta V divided by R3, and delta V divided, I've got an error there. That's R2. I'll fix that. It should be R1, R2, and R3. So I'll fix that. I've got it right here, 10 divided by 45, 10 divided by 45, and 10 divided by 90. Well, we get 0.222 amps, 0.222 amps, and 0.111 amps all added together. You add them, you get 0.55 milliamps. Well, wait a minute, that's different than the other one. That's just a round off error. We get 556 milliamps as opposed to 555 milliamps. That just comes from a round off error. Not to worry about it. Okay. Now, what if we have combinations of series parallel? Well, you have to do it in parts. Like if I would say, well, add these two in series, well, you can't because it branches off into a parallel. So you have to combine this R2, R3 first and get the equivalent resistance for that. Then you can do these two in series. And if we have it here, well, you can't just put these in parallel. You have to solve for this series section first. And once you get an R equivalent for this series, then you can put them in parallel. Okay, so in the left diagram, the parallel portion of R2 and R3 must be reduced first. Then R1 will be added to the parallel equivalent value to get the total R equivalent. The final equation for the left-hand circuit will be R equivalent is equal to R1 plus 1 over R1, 1 over R2 plus 1 over R3. This here is the parallel, the calculation of the parallel portion, and then added to R1 in series. And when I simplified it, I simply used the shortcut. I believe I told you about the shortcuts. And the shortcut is only valid when you have two resistors. There is no shortcut when you do three of them. It's R2 plus R3. I mean, R2 times R3 divided by R2 plus R3. And that's the equivalent for the parallel portion. Then you add that to R1. Okay. Now in the right hand circuit, this one, we have to take care of this series branch first. R1, the way I have it set up here, make it bigger, you'll see it's R1 and R3 are the two that are in series. So we need to take care of, in the right-hand circuit, the series combination of R1 and R3 must be simplified first, and then the series equivalent resistance would be calculated as being in parallel with R2. And the final equation for the right-hand circuit will be the R equivalent is equal to 1 over R2 plus 1 over R1 plus R3. And part of your exercise as an assignment, when it comes to the submission page, I want you to turn in a sheet where you simplify this R equivalent. Similar to what I did in equation 4, I want you to take equation 5 and simplify it, and you turn it in, and it should be one of your pages on your submission page. Okay? Any questions? All right. Measurements before activating your power supply to any circuit. Please have your instructor approve the circuit wiring of your setup. I think we're only going to have one table. I'm not going to be doing a separate experiment, so we'll just work together, and I'll help you all wire it up. So now, what are we doing? Well, we're going to do first a series. They're very simple. We have the ammeter coming right off the battery, and then we have 3 series resistors. I show the voltmeter. I don't show it touching them because we're going to be moving it. First, we're going to measure the voltage across R1, the voltage across R2, and the voltage across R3. And now that I think about it, I think I should add a column or maybe if you're doing it by hand, y'all can add a column to the data table. Okay. Then we're going to do it in, actually that voltmeter's in the wrong place. It should be over there by the resistor. We're going to put 3 resistors in parallel. I've got dotted lines around each of these because we're probably going to be moving the ammeter to each one. It's not going to be permanently part of the circuit. That's why there's dots around them. We're going to do the same R1, R2, and R3. It's going to be, we're going to use those in a parallel circuit. Then we're going to do a series parallel where we have R1, the 1000, in parallel with R2 and R3. And then we're going to take the R1 and R3 and put it in parallel with R2. And we're going to calculate all the voltages and currents for each of these. See what I don't have somewhere on here, and I don't. I have the I might allow you to just put it on the circuit drawings themselves. I may make the circuit drawings with the values part of your exercise, a part of what needs to be turned in your submission page. Okay, and that's it. So you can use this sheet to do your calculations if you want, and turn these in. And I also think I'm going to want the voltages on these. This one's going to be trivial. It's going to be 10 volts all across. The R1, the R2, and the R3 will all be 10 volts. But these will have different values of voltages, and the same here. It's going to have different values of voltages. This branch, this here, and this here, that'll be the same voltage. And then we have our data to fill out. Okay? Any questions? All right. Let's go ahead and stop the share. Oh, wait. Yes, let's stop the share. And this is our proto board. Now, for a series, it's very simple. I've got one. Let me make sure I've got the right one. Let's take it R1, R2, R3. So R1 is the 1000. We put it on the little spring. The spring. R2 is the 56. We put it there in the springs. And then the 33. We put it in the springs, and now we've got a series string of resistors right there. Okay, parallel, just as simple. Of course, we need to attach all the accompanying wires to do the measurements. But as far as configuring the resistors, we'll have little jumper wires going from here to here and from here to here. And now you can see we have 3 parallel resistors right there, right? And when we want to do a series parallel, well, we can put, I don't know that I did that in the right order. That's okay. We'll fix it when we actually do it. Okay, we jump across here, and so we have a series and parallel. Okay, And when we do the parallel series, we just reverse it. We have one branch here, connect this over here and this over here, and we have the right-hand side of the drawing. Okay, so it's very simple to implement these circuits with our little springboard AC/DC electronic laboratories provided by Pasco. Okay, any questions? Let's get to it. And